the previous lecture we started working with some examples on control volume analysis for entropy transport. We will continue with the problem solving in this lecture as well. So, we refer to problem 7.4. A certain industrial process requires a steady 0.5 kg per second supply of compressed air at 500 kilopascal at a maximum temperature of 30 degree centigrade as shown in the figure. This air is to be supplied by installing a compressor and aftercooler. Local ambient conditions are 100 kilopascal and 20 degree centigrade. Using a reversible compressor, determine the power required to drive the compressor and rate of heat rejection in the aftercooler. Okay. So, let us draw a schematic. This is a compressor, this is ambient air. (20 centigrade) 100 kilopascal. This is state 1, this is state 2 and this is state 3. So, this is 20 degree centigrade 100 kPa, P2 is equal to P3 is equal to 500 kilopascal, T3 is 30 degree centigrade and P3 is equal to 500 kilopascal. So, there is a heat transfer at the cooler, there is a work input to the compressor. So, what is given, let me just write down what is given. M dot is equal to 0.5 kg per second. The compressor is reversible and also we can assume that the compressor is adiabatic. So, normally compressors are well approximated as adiabatic devices. So, for compressor it is reversible plus adiabatic, that means you can write here it is an air compressor. So, if air is treated as an ideal gas, this is very important. So, you can write PV to the power gamma equal to constant, where gamma is the ratio of Cp and Cv. Reversible adiabatic of an ideal gas, not any general thing. So, this leads to Tv to the this leads to T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. This we have used in one of our previous problems. It is very simple, you combine this with PV by T equal to constant. So, this combination gives this one. So, gamma for air is 1.4 if you take constant CpCb. You know what is P2, you know what is P1. So, you can get what is T2 from here, Remember, in these expressions temperatures are to be in Kelvin. So, T2 is 464.6 Kelvin. Now, you apply the first law for the compressor. So, if you apply first law for the compressor, there is no heat transfer, neglect changes in kinetic energy and potential energy. Okay. Heat transfer is 0, let us call it Q dot C for compressor. So, W dot C is m dot into H1 minus H2. You can approximate it as m dot Cp into T1 minus T2. Okay. So, you can substitute the values. Cp for air is 1.004 kilojoule per kg Kelvin. So, this will be minus 86 kilowatt. So, that is the first question, power required to drive the compressor and rate of heat rejection in the cooler. So, now you apply the first law for the cooler. So, Q dot plus m dot into H2, here the inlet is 2 is equal to m dot into H3 plus W dot. There is no heat transfer for the cooler. See, it is the same first law, you have to just see what is inlet and what is exit. For the cooler, inlet is 2, exit is 3. So, from here you can calculate what is, so again this is minus 102.5 kilowatt.
So, we could have used minus integral VDP as well, right, for calculating the work.
For calculating the work,
Input to the compressor.
for input to the compressor, oh this one. So, this one, yes, exactly the same, this is minus integral VDP only. Okay. Problem 7.5. Two flows of air are both at 200 kilopascal. One has 1 kg per second at 400 Kelvin and the other has 2 kg per second at 290 Kelvin. These two flows are mixed together in an insulated box to produce a single exit flow at 200 kPa. Find the exit temperature and total rate of entropy generation. So, this is the first problem that we are encountering, numerical problem, where we are talking about an irreversible process with entropy generation. So, let us see how we tackle it. Let us go to the board and draw the schematic of this problem. So, any problem before solving, if you draw the schematic and write what is known, then that helps you to solve the problem very easily. So, there is one stream of air which comes at state 1, there is another stream of air which comes at state 2, these two streams mix. So, this is like a mixer and finally that comes out is state 3. all pressures are 200 kilopascal. So, this entire thing is constant pressure process. Pressures are important not for calculating the or using the first law, but for using the second law, because entropy change will be a function of pressure, even if it is an ideal gas. So, these are all 200 kPa. M dot 1 is 1 kg per second, m dot 2 is 2 kg per second, so m dot 3 just by mass balance is equal to m dot 1 plus m dot 2. So, that is 3 kg per second. So, now you apply the first law. There is no net heat transfer, right. The box, the entire thing takes place in a box which is insulated. So, q dot which is 0 plus m dot I h I, summation of m dot I h I, that is m dot 1 h 1 plus m dot 2 h 2 is equal to m dot 3 h 3 plus w dot. There is no work here, it is insulated, so there is no heat transfer. Therefore, you can calculate, so m dot 3 is m dot 1 plus m dot 2, right. So, you can write m dot 1 into h 1 minus h 3, that is Cp into T 1 minus T 3 if you assume constant Cp, plus m dot 2 h 2 is Cp into h 2 minus h 3, this is 0. So, this will give you what is T 3. So, T 3 is 326.67 Kelvin. Okay. Then you apply the second law. So, second law when you apply, the change in entropy. So, exit minus inlet, this is exit and these are inlet. So, m dot 3 S 3, this is exit minus inlet. There is no heat transfer, and m dot 3 is m dot 1 plus m dot 2. So, m dot 1 into S 3 minus S 1 plus m dot 2 into S 3 minus S 2 is equal to S dot J. If you consider constant CPCV ideal gas, this is Cp ln T 3 by T 1 minus R ln P 3 by P 1. This is Cp ln T 3 by T 2 minus R ln P 3 by P 2. All the pressures are same, so this term is 0 and this term is 0. Temperatures are known, so you can all remember, again I am repeating, all temperatures should be substituted in Kelvin. So, if you do that, you can calculate what is entropy generation rate, which is 0.0358 kilowatt per Kelvin. This is rate, So, kilowatt per Kelvin. We will work out one more problem in this lecture before we stop. Problem 7.6. One type of feed water heater for preheating the water before entering the boiler is based on the principle of mixing of the water with steam that has been bled from the turbine. So, I will explain you what this feed water heater does. See, boiler requires energy for getting converted the fluid from or the water from low enthalpy to high enthalpy, okay, because the enthalpy at the outlet of the boiler is utilized to drive the turbine. So, the heat input to the boiler is expected to be less if the water already enters at a high enthalpy. So, how that is possible? You bleed a part of the steam from the turbine which is at higher enthalpy than the water that is circulating out of the pump, and then you mix it with the boiler inlet fluid. So, if you mix it with the boiler inlet fluid, so the boiler inlet fluid may have a low enthalpy intrinsically, but you bleed a part of the steam that is already at an elevated temperature from the turbine and mix with that. This mixture will effectively have quite a high enthalpy, so that the energy required to drive or energy required to heat the steam in the boiler to convert it to a superheated state is much less, and this mixing process can take place in a device called as feed water heater. So, let me draw the schematic of the feed water heater. Feed water heater. So, this is 1 MPa 40 degrees centigrade, this is state 1. State 2 is 1 MPa 200 degrees centigrade. This is already at a higher temperature. It is already at a higher temperature because it has been bled from the turbine, and the net final state is 1 MPa 160 degrees centigrade and 4 kg per second. These two flow rates are not known. So, from the thermodynamic states given and the first law we can find out the mass flow rates of 1 and 2. How we can do that? First you apply the mass balance. So, this is our control volume, mass balance, m dot 1 plus m dot 2 is equal to m dot 3. Okay. Then first law, q dot plus m dot 1 h1 plus m dot 2 h2, this is summation of m dot I hi is equal to m dot 3 h3 plus w dot. So, here there is a heat exchange internally, externally there is no heat transfer. So, this is 0, there is no work transfer, and in place of H1, H2 and H3 you can substitute properties from the table. So, you can calculate. So, what is required? What is m dot 1 for example? M dot 2 you can write m dot 3 minus m dot 1 from here, and m dot 3 is 4 kg per second. So, from this equation only unknown is m dot 1, which is 3.237 kg per second. What is asked? Calculate the rate of net entropy increase or entropy generation rate. So, for that we have to apply the second law. So, the net change of entropy, that is m dot 3 S 3 minus m dot 1 S 1 plus m dot 2 S 2 is equal to q dot by T plus entropy generation rate. This is 0. S 1, S 2, S 3, these are all from property table at these conditions. Okay. So, at these conditions from table, so this is water. So, from steam table at these conditions you can calculate from the table S1, S2 and S3. Mass flow rates are known, and this will give you what is rate of entropy generation. So, entropy generation rate is 0.8097 kilojoule per Kelvin. So, rate of entropy generation kilowatt per Kelvin, right. Right, kilowatt per Kelvin. So, we have worked out 3 problems in this particular lecture. We have worked out a few other problems in the previous lecture. We will work out more problems in the subsequent lectures, but I want to give you a broad structure of these problems concerning entropy. So, invariably, although the problem is related to entropy, you also invoke the first law. There is absolutely no problem that we have solved where bypassing the first law we can just utilize the entropy transport to solve the problem. The reason is that entropy transport is very important, but we also have to make sure that the problem solution satisfies mass balance and energy balance. So, if we calculate entropy transport without satisfying mass balance and energy balance, that remains physically unrealistic, and that should be the message from the problem solving desk so far, that for solving the entropy transport problems we commonly have to combine first law and second law, sometimes along with that the TDS relationship, and that gives a structure of the basic equations that you need to solve the problems related to entropy transport across a control volume. We stop here today. Thank you very much.